So today, we're finally getting into redox. And what redox is going to do is it's going to completely and totally dynamically change the way we look at reactions. I'm going to go ahead and tell you, this is really odd and complicated in the beginning because it's something you've never seen before. If you hold on for the ride, I can assure you, after we do several of these, it's going to get really, really easy. Okay? The problem is that it's very methodical. Some of you don't like to follow processes. Some of you just want to kind of willy-nilly it and do it all on your own. This is the point in time which I need you to not invent new ways to do something. Several of you, I need you to just accept the fact that there is a process and it has to be followed. If you can somehow simplify it, I'm all ears. But we're not redoing the whole thing. Okay? So, let's first start talking about what redox is. Okay? What does redox stand for? Reduction and oxidation. We already know that fancy little acronym called oil rig, and that's what all of this is going to talk about. So, electrons are transferred. Dustin, will you do me a favor? Will you come shut this door? Okay? And what does it mean by transferred? Yes. Actually, both. Yes, both. Thank you. No. I meant the other. Just leave that one. Good luck. You're going to spin there. Okay. So electrons are transferred from one ion to another. Spontaneous. What does spontaneous mean? It happens on its own. Is there any force from the outside world? Okay? Like you guys would spontaneously eat whatever you can get your hands on right now, right? I would not have to force it down your throat. Now, there are a few things that you probably wouldn't eat. If I pulled out some rutabagas or some collard greens, well, some of you like collard greens. Rutabagas, you may kind of throw up a bad fist at me. Okay, so here, I told you. I told you. So here's what I need you, go ahead. Huh? Yeah, moved from one eye to the next. I told you. Now, I need you to write this term, and when you write this term, you're going to want to throw a stick at me. But just hold on. Actually, I want you to write this word somewhere by the term spontaneous. I'm going to come off of this page and go here. Told you. Just let it shut. Nothing. Thermodynamically favorable. This is what you need to write beside spontaneous. Write it above or below the slide and draw an arrow to it. For some odd reason, the new AP curriculum 3 years ago has decided to eliminate the term spontaneous from their vocabulary and replace it with this beauty. Now, for the modern world, or for the basic world, spontaneous works just fine. It means it happens without outside interference. However, apparently for the AP chemistry people, okay, this is the new way that it must be stated. Thermodynamically favorable. And I get it. It makes sense in the thermodynamic world in terms of energy. Thermodynamically favorable means that it proceeds to a position where energy is utilized in a positive way. That means it can produce energy, right? Is any energy needed to force this reaction to occur? No. That's why it's considered thermodynamically favorable. It proceeds in a favorable direction that produces energy, not requires energy. Does that kind of make sense? Now, you can get your giggles out of the way because I refer to this term as TF. Go ahead and giggle. Thermodynamically favorable is TF. It's a lazy way of saying WTF. Okay? So, Again, if you ever hear me ask, is a reaction TF? I'm not referring to WTF. I'm referring to thermodynamically favorable, even though some of you are thinking otherwise. Okay? But I'm wanting you to see this word because in the past few years, this terminology has been utilized. Is the following reaction thermodynamically favorable or not, and why? And we will talk about how you will know later on. We're going to talk about this factor right here. And if you want to go ahead and add this. Now, this is not phonetically correct, but that's okay. I really don't care. I call it the geek factor. I just enunciate the E. This is... Who cares? I call it the geek factor. And what the geek factor is if it tells you if a reaction is thermodynamically favorable or not. Okay, and I know what you're thinking, what does geek have anything to do with it? Geek is an acronym. G stands for something, E stands for something, and K stands for something. Okay, it's an acronym. Okay, no, G, and I'll go ahead and tell you, we'll get to all these things later. Again, here are some of these Velcro things flying your way. G stands for Gibbs free energy. Gibbs, G-I-B-B-S. Okay, G-I-B-B-S, Gibbs. We're going to get to it later, so I mean, it may behoove you to write it down. Okay. Behoove. It would behoove you to write this down. What's the language of origin? Gives free energy. Now, this next one's going to... Go ahead. Yeah, I would. Okay. E, and this was going to be the weird one. Okay. Cell potential. And this one's going to make even less sense. And again, don't worry, don't just accept it. It is the one thing about chemistry that drives me bananas, is that none of the letters ever represent what they're referring to. Yeah. We're going to get into R, which is the rate constant. Or, excuse me, baby K is the rate constant. It's little k, lowercase. So this... Yes. So, I've never taught you any of this. Go ahead. Exactly. We'll talk about that later. I know, and that's... Can I talk? Shh. One of the things that Mary Beth just brought up is she's accurate in saying this, is what happens if you have the equilibrium constant and Kelvin in the exact same question. You are right. It is aggravating. There's nothing we can do. It's your reading of context analyzation. When you read it, you have to know what it's referring to. Now, Mary Beth, I'll tell you this. It will more than likely say in the equilibrium constant is K equals blah, blah, blah. Okay, and the temperature will be in a way that it's clearly stating the temperature. Okay, so don't worry about them not telling you what it is and all that kind of stuff. Okay, so these are what the geek factor represents. So G is Gibbs free energy, and if you want to write this out, and I'm going to kind of run out of room, the G will come into play in thermo. The E will come into play in electro, and the K will come into play in equilibrium, obviously. Okay? Not thermo. Okay? And these three things, equilibrium, like K comes in during the equilibrium topic. Okay? So, when we talk about something, if it's thermodynamically favorable or not, these are the only three things that can tell you if something is thermodynamically favorable. And it's not the how is it, it's yes or no. Is it thermodynamically favorable? And the way you can tell is we ask ourselves a question about one of these three. Do y'all want to know how to tell? Let me go ahead and throw it at you. This is how you tell. If G is negative, it's thermodynamically favorable. If E is positive, it's thermodynamically favorable. And this is always the weird one. If K is greater than 1. It is very specific. And again, you don't know any of this, but I can assure you, all of this is coming your way. I don't want you to know how to do it, what to calculate, when to calculate, where to calculate. I just chunked a boulder at you, okay? A boulder of Velcro. Now, here's the deal. Here's the cool part. If you know one of them, you know them all. If you know one of them, you know them all. So if I tell you G is negative, automatically E is positive and K is greater than 1. If I tell you that E, and listen to how I ask this, if E is negative, then you know G is automatically what? It's the opposite. So when you know one, it's not theoretical, it's mathematical based, and we'll talk about how it's mathematically based later. Go ahead. All right, so negative and positive is in reference to 0. K is in reference to 1. Yes. So less than 1, yes. All right. Again, we'll come back to all of this. I know that's kind of a lot, but we'll get there. Very little. But you've seen this. You've seen Gibbs free energy in biology. Have you seen Hess's law? I know you've seen this one before. I'm only talking to Chance and Ryan because they've seen this before. I doubt Miss Huff used this language. You've seen that. But, yep. This is one of the equations we'll talk about in thermo. Ryan, you should have seen this in AP Bio. The way that I say this is called ghetto homies take speed. Okay. Ghetto homies take speed. As in the drug. Okay. All right. Now, here's what we say. Spontaneous redox reactions. Now again, spontaneous is going out the window. We're talking about thermodynamically favorable, or TF. Thermodynamically favorable reactions can transfer energy. Now, that galvanic or voltaic cell, out beside that, please write, makes a battery. Okay, galvanic, voltaic. Stop, Dustin. Most people don't know that. Makes a battery. I agree with you. It's Voltaire, yes, I get it. Okay. But a battery powers a light bulb, right? Can a battery power a light bulb? All right. Now, there's two ways it can transfer energy. It can transfer it in electrical energy, or it can transfer it in heat energy. So do me a favor. Now that we've already seen this, the electrons is going to be, and again, I know this is going to look weird to you, but write it just like this. It's a curly QE with a little degree symbol on it. Yes, we'll talk about that in a minute. That, you're going to start seeing me write this quite often. I write my E for cell potential just like that. And if I handed you an AP textbook, I can assure you every single one of those are going to be written just like that. The reason why is it differentiates it from other E's. When you see the curly QE, you know it is cell potential. You don't have to think. With the little degree symbol, we'll talk about the degree symbol later. I'm giving you visual stimulus right now, and we'll come back to all that stuff later. That's why exactly. Okay. Now, heat, this is referring to our delta G, which is our Gibbs Fe, and again, free energy. So delta G. Now, I know the geek factor is a little strange, but these are two of them. Now, Justin, you asked a minute ago, can a reaction produce both electrical and heat energy? Absolutely. Do things running on batteries get warm? For sure. Okay. Well, it can do both at the same time. Okay. Now, non-spontaneous reactions, and this is kind of where it gets weird. If spontaneous reactions are thermodynamically favorable, then how would you say non-spontaneous? Non-thermodynamically favorable. Okay, so that still should make sense. Redox reactions can be made to happen with electricity, and this is called an electrolytic cell. Now, just a minute ago, up here by galvanic voltaic, you wrote what? Makes a battery. Down here by electrolytic, please write uses or needs or requires, however you want to phrase it. By electrolytic, it requires a battery, essentially. Okay, so just write it. It's got a very I can't think of right now. Yes, yeah, its electrical capacity is very great. Okay. Now, so here's what's going on in redox reaction. So let's look at this. So oxidation reduction, we see calcium is oxidized. Now, notice what it says right here. Do me a favor and write oil above that. Oil. Oxidation is a loss. Okay? So what's happening is that calcium is going from Ca solid to what? It's going to the ion. Okay? So what's happening here is that piece of calcium is losing 2 electrons to the atmosphere. And guess who is there to snatch up those 2 electrons? Oxygen. Very good. So oxygen is going through the rig part. Okay? So here's the next part. Stay with me. Okay? So the O2 minus is going to what? Okay? So 2 O2 minuses are going to O2. All right. 1 oxygen atom. Excuse me. Pause for just a second. Ignore that last part. Erase that. Just erase that part. That's why you don't write in pen. Do you need a pencil? Do you need a pencil? Okay. Okay. Yes. That. Yes. Here's what's going to happen. Stay with me. Let me rewrite this. O2 goes to 2 O2 minus. I wrote it backwards. That is right. So write that down. Yes. Here's what happens. Do you agree that group 1 and group 2 are very reactive? Okay, if you drop group 1 or group 2 in water, it reacts, right? Now, so it naturally will also react. Don't mess that up, please. Let me talk. So what naturally happens is that the metals will naturally react with the oxygen in the air, okay? Because oxygen is an oxidizer, right? Now, would group 1 or group 2 react more vigorously with oxygen? Group 1, they are more highly reactive than group 2. In fact, if you take a piece of group 1 and it's very soft metal, you can cut it like butter. When you cut it, you can actually see the very shiny, bright silver part. I've showed you one of those videos before. And so you can actually take it, and as soon as you cut it, it already starts to oxidize. It tarnishes or rust, if you will. Okay? So it's starting to turn that darker color. So if you notice, it's very hard to tell in this picture. But can you tell how it's kind of silvery white here? And then over here, what color does it turn? It's more of a darkish gray. That gray color is the oxidizing coat of those calcium chips. Okay, so if you notice here, this right here is going to be pure calcium. And then notice what happens over here. What is happening to that calcium? It's being reacted by oxygen. Okay, here's an important question. Is the mass of that going up or going down? Up. The reason it's going up is because is any of the calcium leaving? So what are you doing? How many oxygens? So you're gaining 2 oxygens for every 1 calcium. Stay with me right here. Do you agree that we had 1 calcium? We are gaining 2 oxygen ions. The reason why, you know what? So you are right in this. I did misstate that. That for every 1 calcium you gain 1 oxygen because it's a 2 to 2. My apologies. Okay. All right. For every 1 calcium you gain 1 oxygen because it's a 2 plus and a 2 minus. Yes. Yes. Let's just move on. Now, so here's another type of reaction. We have solution reactions. So that one was more of an atmospheric reaction. This one can be a solution. So we've got magnesium solid, right? Okay. So we're going to take some of that solid. We're going to drop it in some hydrochloric acid. First of all, what do we know about hydrochloric acid? It's strong acid, okay? So we've got 2 HCl, and what is going to happen is it's going to react, and we're going to get magnesium chloride, and we're going to get hydrogen gas. Now, with your eyeballs, how can you tell that you're getting a gaseous byproduct? Bubbles. Now, when you do the reaction, you should be able to know what the gaseous byproduct is, because what type of reaction has just occurred? Single replacement. My question is, why in the world is this little bitty 2 here? Very good, it's a diatomic. Okay, so what's going to happen is this hydrochloric acid is going to pretty much essentially eat away at the magnesium. Now, the thing about solubility rules we've talked about here is we've got that AQ thing there. How do you know that a precipitate is not formed? Chloride is soluble unless with whom? Heavy metal bad guy, silver, mercury, and lead. So is this a heavy metal bad guy? No, so what you're going to get is you're going to get a busted effect. You're going to get Mg2 plus and 2 Cl minuses, right? So if you notice right here, all of that floating around, have some of those silver spheres fallen off into solution? Yes, okay? Notice, what are these little white spheres right here? Those are the hydrogens. Okay? So again, there's 2 of them. Okay? Yeah, there's 2 of them. They're 2 little spheres connected together. Okay? And so that's what is going to happen in this particular reaction. You drop it in, the hydrochloric acid is going to have a single replacement. The magnesium ions are going to drop off into solution. You got one there, you've got one there. Then over here you got 1, 2, 3, 4, 5. So you've got all that stuff going on, right? Okay. So if I have enough hydrochloric acid to react with the magnesium, would all of the magnesium ribbon disappear? Yes. It will be 100% dissolved in solution. But what happens if the hydrochloric acid is the limiting reactant? What's going to happen? Are you going to have a little bit of the ribbon left over floating around at the bottom? Yeah, it'll be a solid piece of ribbon floating around. So my question to you is did a redox reaction occur? Did oil rig occur? It's important for you guys to know how to do oxidation numbers. Now, I came and taught one of y'all's classes last year on oxidation numbers. I know that was 2 years ago. So as far as oxidation numbers, this may take, for you guys that had me, this is going to be a breeze. For those of you that didn't, it may take you a little while to figure this out. But I can assure you the math of it is very simple. But there's 4 rules really that you got to know. Okay, and we'll talk about those 4 rules. Yes, ma'am? Okay, go ahead. No, I think hydrofluoric is more dangerous. Strong. All right, so Dustin, did you ever find it? Okay. Gotcha. Okay. All right, so here's the deal. This what I just gave you is the rules of how to calculate an oxidation number. Now, some of you know how to do this. You don't even need this sheet, and that's awesome. But some of you may need this as a help or a refresher. So what we're going to do is we're going to look and see if a redox reaction occurred in this particular reaction. So I'm going to this. No. Yeah, it was. It was on the summer when y'all traveled around. The second day of school, I wasn't here. All right, so let's look at this. First of all, what are oxidation numbers? It's the charge on the ions in an ionic compound that reflect the electron distribution of the compound, which means how many electrons each atom is sharing specifically. Okay, it's not the charge, it's how many they're going to share. So here's the rules for assigning oxidation numbers. Okay, in general, when assigning oxidation numbers, shared electrons are assumed to belong to whom? The more electronegative element in each bond, and that's going to come into play a little bit later on. So rules. Number one, determine if the compound is neutral or charged. So let's look at Mg. Is it neutral or charged? It is neutral. So what do we set it equal to? Set it equal to 0. So again, that's number 1A and 1B. Number 2, if the atom is in its pure elemental form, what about Mg? Is it in its pure elemental form? So what's this oxidation number? 0. Now do me a favor. Look up there at the very, very, very tippy top. Do you notice where it says oxidation numbers in red? It's a circle. Where do your oxidation values go? At the top. So the oxidation number for Mg is 0. Okay. Let's go to our next one. HCl. Is it charged or neutral? Neutral. I'm going to make it equal to 0. Okay. So let's go to number 2. Atoms in pure elemental form. They're by themselves. Is anything by itself up there? Anything by itself? No, there's a pair. I'm just looking at this compound. Number 3, do you see parentheses? Nope. Number 4, is it an ionic compound? Is there metal present? Do you see a metal? No! HCl. We're still right here. Is a metal present? No. Number 5, fluorine. Nope. 6, oxygen. Nope. 7, hydrogen. Yes, hydrogen has an oxidation number of +1 in all compounds containing elements that are more electronegative than it. Exceptions when hydrogen is with a metal. Is hydrogen with a metal? No, so what's this oxidation number? +1. Now, because it's neutral, hold that thought. We're going to figure this out. Now, go up there to the very tippy top. Find the down arrow. What do you do when you go down? Multiply. What is +1? And here's the crazy part. What am I multiplying it against? I'm multiplying it against the subscripts. Stay with me. I promise you, the more you see this, you're like, God, this is super easy. What is +1 times 1? +1. Now, let's make this basic algebra. What do I need to make +1 equal to 0? Well, that was easy. Now, go back up there to the tippy top. What do you do when you're going up? Divide. What am I dividing by? The subscript. What is -1 divided by nothing? -1. Because I've got to get my oxidation numbers. Yes, no, maybe? Yes. Okay. All right, go to the next one. Just hang on for the ride. No. Now, number 1 again. Now we're going to MgCl2. First question, is it neutral or charged? Set it equal to 0. All right, number 2 is anything by itself. Number 3, do you see parentheses? Number 4, is it an ionic compound? It's the first element of metal. So look at what it says. If it's a metal, its oxidation number comes from its charge. What group is Mg in? 2. So what's its charge? 2+. Okay? Now we do our math. I promise you, you'll have them memorized within the first 5 or 6 times you do this. Guys, do you memorize these really quickly? I'm telling you, you do. You're not going to forget them. Okay, sir. Wow, that's a lot less than I was thinking. Okay, all right. Okay, all right. So as I go down, what do I multiply against or by? 1. So positive 2. Now this makes sense. What am I? How do I get a positive 2 to be a 0? Negative 2. Now this time, very good. So negative 2 divided by 2 is negative 1. Okay. Any question? We good on that one. Now let's go to H2. Rule number 1. Determine if the compound is neutrally charged. It is neutral. Set it equal to 0. Number 2. Atoms in pure elemental form have an oxidation number of 0. They are by themselves. Is H with anything else? No. Now look under this. It says examples. All atoms of sodium, which is Na, oxygen, O2, phosphorus, P4, sulfur, S8, have oxidation numbers of 0. Notice the 2, 4, and 8. They are all considered what? Elemental. Hydrogen is called a what? A diatomic. Okay? Okay? So, because it's elemental and diatomic, it's going to have an oxidation number of 0. Does that make sense? Now, here's the cool part about redox reactions. Can you have one without the other? No. If you have an oxidation, must you have a reduction? Yes. Okay? So, I'm going to write this up here. We said oil rig. Oxidation is a loss of what? Here's where it gets kind of weird. Okay? I don't like doing oxidation first. I like doing rig first. Okay? Because reduction is a gain. No. Stay with me. It's a reduction is a gain. So it's a gain of electrons. So what has to happen to its oxidation number? It goes down. That's why I do reduction first. So we're going to look up here and we're going to find one element. Did one element go down in value? Hydrogen went from a positive 1 to a 0. It's from the reactant side to the product side. So do me a favor. So we're going to go and we're going to do this. So hydrogen went through reduction. Does that make sense? Now let's look at the opposite. Oxidation is a loss. But this is why it's weird. This is why I want to do reduction first. It's a loss of electrons. So what happens to its value? It goes up. So we need to find an element that goes up. Magnesium. Very good. So magnesium is going to go through oxidation. Okay? Reduction. It is a red line. I just say redox. Reduction, oxidation, redox. Okay? Does that make sense? Okay? Everybody good on this? So this is a single replacement reaction, but it is also a what? A redox reaction. To be honest with you, whenever we get used to this, you'll be able to look at it and not even do any of all that number stuff you'll do in your head. I can assure you it will get easier. Okay? Alright, so let's move on and let's look at the next one. So, oxidation and reduction, an old memory device for oxidation. Again, I like oil rig. This is Leo says GER. So if you like this one better, it's whatever. Leo says GER is lose electrons is oxidation, and gaining electrons is reduction. It's just a backwards way of saying it. Okay? Oil rig. It says electrons, yes. Okay? Now, so my question is here, if we start gaining and losing electrons, are the size of our atoms going to change? Yes, so notice what it says, oxidize. Remember, that's oil rig. Oil, oxidation is a loss of electrons. Your oxidation state increases, which means the charge goes up, and it's a reducing agent. Do me a favor, that very last line where it says reducing agent, cross that off. Even it, And in the right column, where it says oxidizing agent, cross that off. Okay, so here's the good news. In the old AP exams, that was one of the things you used to have to know. There is no longer a question about oxidizing and reducing agents. Looking at it, though, again, if it's oxidized, which agent is it? Reducing. It's backwards. That's why I think they got rid of it. I think it was too confusing for students. So notice what happens. We've got M and we've got X. If M loses its electrons, X gains it. Okay? So if you gain something, what should happen to your size, theoretically? It should get bigger, and that's why it gains. Okay? Does that make sense? Also, if we really, really, really want to get down and dirty with it, we could talk about this. Don't ask. Don't ask. All right, actually, let me give you, I'm not going to explain what it is. I'm just going to give you an example. Mason, if I sent you up to Slingliff right up the road and I sent you out to PE or to recess with 10 kindergartners, and I said, Mason, I said, you are the perfect person to handle 10. Like, whenever you've got 10, everything's okay. All right? My question to you is, what happens if I send 2 little Johnnies out there on the playground with you? The perfect number is 10. Well, I've just added 2. So what now happens to the ability of them to get farther out of your vision? It's easier, right? So think about it. I added 2 electrons to your playground. What has now happened to the distance of your playground? It's gotten a little bigger. So what does Zeph have anything to do with that? Consider yourself the nucleus. You're trying to hold all these electrons into you, right? So the more electrons we add to your atom, what happens to the size of your playground? It gets bigger and bigger. So let me think about it from this perspective. Let's say I sent you out there with 10, everything's the perfect size. And then I bring 2 little Johnnies back in. Now how many you got out there? You got 8. So now what happens to your vision field? What can you do with keeping them? Thank you. It makes it a little bit smaller, right? So if you gain things, it's got to grow a bit because you can't control it as much. You're only by yourself. But what happens when I take 2 away from you? It's easier to control. So in a very basic way of explaining it, that is what Zeph is. And what Zeph stands for is effective nuclear charge. It's how effective the nucleus is in holding the atom together. Yeah, right. All right, go ahead. Yeah, I'm not going to go into all that, though. All right, so oxidation rules. Again, this may kind of help you out. This is just everything explained in words. That oil rig, we know oxidation is the loss of electrons. Do me a favor, if you have a highlighter, you circle stuff, write or circle that part right there where it says increase in charge. I know it's backwards. So if you think of losing an electron, you think of an increase in charge. So can I give you another mental way to think about this? If you lose weight, does it make you increase in happiness? Yes, for most of us. Okay? If you're 800 pounds, would it make you happy? Yes. Okay? So the way to think about this is oxidation. Okay? So if you go out there and exercise, if you lose weight, you should gain happiness. Or you increase in charge, you increase in happiness. But if you reduce your exercise, then you gain weight. You gain weight, which makes you reduce in happiness. So as crazy as it sounds, whatever makes your brain connect the dots. Yeah, the reduction of charge, yeah. Okay, the rest, and the last 2 things, if you want to just put a line through it, you can scratch that off, and you can scratch that off. Oxidizing agent, reducing agent are no longer a part of the exam, but I just want you to know that if case for some reason you ever take this in college, and they say reducing agent, oxidizing agent, I want you to have heard the word before. And I'm going to set up something in a few minutes that's going to make it a little bit easier. Also, if you for some reason lose that sheet that I gave you just a second ago, this is the rules in your notes. It's not as good of a set of rules as what I gave you guys, but it'll work. It's kind of the same concept. I put time and effort into simplifying it over the years to make it a little bit easier. Y'all want this? Okay. All right? We're good there. Now, so here's a question I always get at the beginning of the year in honors chemistry, and I never want to talk about it, but I do talk about it in honors chemistry, is what is the difference between charge and oxidation number? You want another one? Here. You want another one? Okay. So what a charge is that they're ions. Write this down. Electrons, actually, hold on. Charge are ions, so write ionic beside it. Okay. Charge equals ions, and then write ionic. Yeah, beside that. So a charge only refers to an ionic bond. Only refers to an ionic bond. So that's why it says you can't have a charge with a covalent bond. However, oxidation numbers, they are more encompassing than just a charge. So an oxidation number can be applied to both covalent and ionic substances. Okay? So when we talk about an oxidation number, we're referring to how does that compound fit together. What are the electrons doing with everything that's around it? Okay? So again, it's kind of a weird way to think about it, but this is just kind of a, it helps. Okay? So here's my question. I'm gonna leave the Lewis structure off for just a second. What I want you guys to do is to do the oxidation numbers for these 5 compounds. If you need the rules, follow them step by step. This is where your foundation has to be built. We'll do the Lewis structures in just a second. I spend time here because I think it's important. All right, so looking at number 1. My first question, is it neutral or charged? I'm going to set it equal to 0. Is anything by itself? Okay, guys, y'all listen to me real quick, okay? Nothing's by itself, right? Do you see any parentheses? Do you see a metal? Do you see a fluorine? Do you see an oxygen? All right, -2 multiplies I go down, so I've got -4. So what else do I need besides -4 to make it back 0? +4. Is there anything to divide by? +4. Those are my 2 oxidation numbers. Okay? The next one, SF6. Set it equal to what? Why is it 0? It's neutral. Is anything by itself? Is there any parentheses? Is there a metal? Is there a fluorine? What is fluorine always? All right, -1. As I go down, what do I do? So -1 times 6 is -6. All right, what do I need to make that 0? +6. Is there anything I need to divide by? Nope, so it's +6. Those are my 2 oxidation numbers. All right, moving on to NO3. Neutral or charged? Set it equal to 0. Is anything by itself? Do you see parentheses? Do you see a metal? Do you see fluorine? Do you see oxygen? What is it? -2 times 3? What do I need to make that? +6. +6. You with me? Zava? You good? Sure? Okay. All right, I'm gonna write this over here. Makes it easier to see. KMnO4. Okay. Neutral or charged? Set it equal to 0. Is anything by itself? Are there any parentheses? Do you see a metal? Who? What group? +1. What do I do multiplying down? +1. Are there any fluorines? Any oxygens? What is it? Multiply down. What do I need to make it neutral? +7. What do I divide by? Nothing. +7. Exactly. Is it getting easier? Do you see the method? Do you see the method? Okay. What's wrong? Yep, it's transition. All right, so let's go to the next one. The next one is, can't even see that. Cu2SO4. All right, neutral or charged? Set it equal to 0. Is anything by itself? Is any parentheses? Do you see a metal? Who? Copper. Now, this is the tricky one. Which copper? 1, The reason it's 1 is because if I pull back, would that be -2? When I pull up, that's going to be +1, right? Okay, so I'm going to eliminate that. Now, next question. Multiply, go down. +2. Do I have a fluorine? Do I have an oxygen? -2, multiply going down. What do you need to make it neutral? +6, +6. Any questions on those? All right, so let's go to the next slide. We'll come back to Lewis structures in just a second. Now, this one, first of all, does anyone know the name of this thing? No. Very good, it is oxalate. What is different about all four of these as previous to others? They're charged. This is what makes them a tad bit more complicated. So, is it neutral or charged? What do I set it equal to? The value of the charge, which is -2. Okay? Is anything by itself? Do you see parentheses? Do you see a metal? Yes or no? Do you see fluorine? Do you see oxygen? What is it? Multiply going down. Now, this is one where you actually got to think. I need to make -8 -2, not 0. So what is it? +6. Now it's +6 what by 2? What is +6 divided by 2? +3. Does that make sense? Yes, no, maybe? Okay. All right, looking at the next one. Nitrate. Is it charged or neutral? Set it equal to -1. Is anything by itself? Do you see parentheses? Do you see a metal? Do you see fluorine? Do you see oxygen? What is it? -2 times 3 is? Again, you got to think here. How do I make -6 -1? +5. Okay, do I divide by anything? Nope, +5. Very good. I think you guys are starting to catch on, aren't you? I told you, I have no fear in you not picking this up. This is really basic. Okay, nitrite, charged or neutral? -1. Is anything by itself? Any parentheses? Any metals? Fluorine, oxygen, negative. Multiply. How do I make -4 -1? +3 and +3. I think you guys are figuring that out, aren't you? Okay. Can anyone tell me without even doing the math what the chlorine is going to be in the next one? Very good. It's got to be equal to -1. I know that oxygen is going to be -8, so I need it to be -1, so it's got to be +7. Okay. All right, so with a little bit of time I have left, Esteban, come bring everybody one of these, please. Because I need you to go back a slide, and this is the part where if you have a sheet of paper or if you want to do it somewhere else, this may be beneficial to do it here. What we're fixing to do is we're fixing to do the Lewis structure rules. Okay, we're going to draw the Lewis structure for these things. Some of you need to do this again. Some of you don't, and others of you have never done this. So we need to make sure we clear this up very quickly. These 2 sheets of paper are going to be very beneficial to you over the next several weeks. Seriously? Holy bananas. Well, I still have it. That's fine. All right, so let's talk about the rules. It says list each element in the formula and how many of each are present. So here's what we're going to do. Whatever we run out of time on, I only want tonight you to try to draw these the first 3. You can't do D and E. So whatever we don't finish, use these tonight and try to draw A, B, and C of whatever we don't finish. Okay? All right. So the first rule, it says list each element in the formula and how many of each are present. So I've got C and I've got O, right? All right, how many of each do I have? All right, I've got 1 and, sorry, not 3. I've got 2. Okay. Then it says determine the number of valence electrons for each element. What valence number is carbon? 4. Oxygen is 6. The valence number. Okay. Determine the total number of electrons for that compound. What is 1 times 4? 4, what is 2 times 6? 12. What is 4 plus 12? 16. That is step number 3. Determine the total number of electrons for that compound. Now look at step A and B. A, remember if it's charged. Is this charged? So I'm going to ignore that. Okay. B, be sure it's not an odd number. Is a 16 odd? No. Why does it have to be even? Electron comes in pairs. Number 4, draw the skeleton structure. Determine the central atom, the atom with the most available bonds and or the least electronegative. Then I give you another little hint. It says who is always in the center and who's never in the center. Hydrogen. So what I'm going to do is I'm going to come over here. I'm going to start with, I got 16 carbons in the center, and I'm going to draw a skeleton structure. It may adjust from this point. All right, number 5. Connect all of the other elements to the central atom with a line. Did I do that? 5A. Subtract the number of bonded electrons from the total number of electrons already calculated. One line is how many electrons? 2. So how many do I have total? 4. So what is 16 minus 4? 12. You with me? Number 6. Give all the outer atoms. Who are the outer atoms here? Oxygen. A full octet. What does octet mean? 8. Except who? Hydrogen. Read, hydrogen. Now, how many does each oxygen already have? So I need 2, 4, 6, 2, 4, and 6. Does each oxygen now have its full octet? Yes. How many electrons did I just use? 12. 2, 4, 6, 8, 10, 12. Now look what it says at 6A. Subtract the number of octet electrons from the remaining electrons available. I had 12. How many did I just use? I just used 12. So how many do I have? 0. Now, here's the problem. Real quick. Read 8. If the central atom is not yet surrounded by 4 electron pairs, does it have its full octet? No. So what do? Convert one or more terminal atoms to lone pairs to a what? A double bond. So what I'm going to do is I'm going to take these 2 off the end, and I'm going to make it a double bond. Does carbon still have its 8? No. So what do? Take 2 from the other side and stick it there. Now does it have its 8? That's CO2. What's the shape of that? Linear. Bond angle. 180. Polar, nonpolar. Nonpolar. Intermolecular force. That is IMF. Very good, LDF. Yeah, the reason it's nonpolar, because look. Yes, SP.